So here we have a ring set up with a penny on top, so there's some mass with some inertia, and our goal is that can we knock away this ring so that it makes it in this container. One idea is that you might just want to hit this from the outside, but if I hit this from the outside, what's going to happen? Isn't this going to bow up and want to make that, put a force on that penny upward? So we want the penny to stay at rest. You know, it will remain at rest until a force acts on it. And potentially, if I just get the ring out of the way, then the only force on it will be gravity. And so it'll only change its motion in that direction. All right, there you go. So here we have what a conceptual physics author calls a dealy bop, and we have weighted clay balls on just a coat hanger. So if you want, you can try to make one of these at home. And there's a reason for those weighted balls, and that is that they have more inertia. So I have this balanced on my head, and I'm looking at one clay ball. How would I look at the other one? How could I see the one behind my head? All right, just like that. So me turning had no influence on this, and we can see that these did not, they wanted to remain at rest due to their higher inertia. All right, so here we have a case where a guy just stopped for a light, waiting for the light, and this taxi cab, he was looking at his phone and texting, and so he didn't see this car was stopped. And what's going to happen if this guy comes real fast and rear ends this other guy? All right, so let's watch this action. All right, so here we see this poor guy lost his head, and the question is, what happened to his head? Did his head, so in whiplash, did his head go backwards because he got rear-ended, is the question. All right, so here we have a case that's opposite from the last clay man who lost his head. The car was forced to move in that case from rest. And here we have a car where it is going to be forced to stop because it's going to run into, let's say, a wall. And we're going to see what happens to Mr. Kitty right here. All right. So, was he thrown out of the car? Was he forced out of the car? Or was there something else happening here? All right, so here I have a bucket filled with water. And so I don't know if you've ever done this, but this is fun to do. So I can have the bucket, and if I get it in motion, I can take and have it go in a circle without spilling out. It isn't that gravity's not working anymore. It's the fact that once water is in motion, it wants to continue in that motion. And if you are in a circular motion, it's going to be tangent to the circle that it wants to keep going. That was its velocity, like right here, its velocity is this way. When it was up high, it was this way. And it wants to continue in that line of motion. And actually, the bottom of the bucket is forcing it into a circle because it would like to go in a straight line according to inertia. All right. All right, so here we have a massive iron ball. And to say that it is massive means that it has a lot of inertia. So this ball has a lot of inertia, so we need to keep that in mind as we do this experiment. We're going to do a few different scenarios. So right here, I'm going to pull on this bottom string. And I'm slowly going to pull and apply more and more force. And let's see what's going to happen. And we know a string is going to break, and the question is it going to break at position B or at position A? And think about the forces acting here. So I'm starting to pull. All right, and we see it broke at position A. And what does that, now why would it break at position A? Was there more tension here? What was happening there? So we have the pull of me on that top string, but also, right, the weight of this ball on that top string. The bottom string only had the force of my pull. All right, so now we're going to do things a little bit differently. So instead of pulling slow, all right, and slow meaning I would give time for this to move, I'm going to pull very, very quickly, and let's see what happens. All right, you see this time the string did not break at position A, but at position B. And realize if I pull really, really fast, and this string got tension in it, felt immediately tension, did this string feel that tension of the pull? What was happening to this ball? This ball resisted moving because it has a high amount of inertia. So when I gave this quick pull, this string broke before this ball even started to move, and the tension was felt by that top string. All right, so here we have a case where we have a head of a hammer that happens to be loose. It's not tight on there. And so there would be a few different ways you'd think that you would have to try to get this on here really tight. But there is a good physics way how to tighten this head onto the handle. A lot of people think you should hit something like this, but instead, this is the physics way. We're going to go like this. And if you look, this is super tight now. You can see how much it has fallen down onto that. And so how is that working? What is being forced in this case? If I go like this, everything is in motion. It hits the table. And what is forced to stop? The handle is forced to stop. What happens to this heavy head? Is it forced to stop? No. So it continues down as long as it can until it truly is forced to stop. And that, in a sense, it doesn't force this onto this handle. Instead, it continues onto the handle while the handle was forced to stop.